So the topic of today is Markov decision processes. This is a topic really close to my heart, and I was hoping to cover at least 2 hours of this, but we'll cover some. The reason it's close to my heart is because this is the field I had my PhD thesis in. This is also the field in which Andre and I have co-written a survey book. I will put up the link for that online. If any of you are able to read any pages of it and find a mistake or something that is not clear, please give me feedback so that I can improve it. So let's talk about this. So you may have seen this figure by now. You have an agent which is interacting in an environment. This environment may have various characteristics, like it may be static or dynamic. The environment may be fully observable or only partially observable. Sensors may be perfect or noisy. My actions may be deterministic or stochastic. My actions may be instantaneous or may take time. And the greenest version of this is where everything is the nicest possible. Like environment doesn't change by itself. I can observe everything. I observe it perfectly. My actions are deterministic. And this is classical planning or deterministic single agent, atomic agent that we have been studying. Now the change that we are going to make, since we are in the uncertain world, is that now my actions are going to be stochastic. So when I take an action, I will not know exactly where I am going to reach. I will be reaching with different probabilities, different states. And this is exactly what we just did in decision theory. So when I build a large plant or a small plant with different probabilities, I was going to reach different points and get different rewards. However, the difference between what we did so far and Markov decision process is that in decision theory we were making only one decision. And this is the important point. We took all our time figuring out what should this one decision be. Build large plant, small plant, no plant. Now, what we are going to do, in deterministic worlds, we have to come up with a sequence of actions to reach a goal. So now, how do we come up with a sequence of actions to reach a goal if we are in an uncertain environment? That is the problem we are going to solve, and that gets modeled as a Markov decision process. Is the high level point okay? Where my goal is far away. I can't reach that in one action. I will have to take multiple actions one at a time and keep going forward, and then I have to reach them.
So that was true in general for search.
But that was not true in the what we just did, where we were taking only one action. Alright, so let us first define the atomic agent for this. So we, as usual, have a set of states, we have a set of actions, and then we have a transition model. We always had a transition model. If I take this operator in this state, where am I going to reach? But now this transition model is probabilistic. I'm going to reach different states with different probabilities. I may have costs associated with these actions. Now notice why we call it a Markov decision process. We call it a Markov decision process because all the transitions and costs depend only on the current state and what's going to happen in the future. And it doesn't matter how I reached this state. That's the Markov assumption. The Markov assumption says it doesn't matter what path you took, as long as you finally reach this state, what's going to happen to you in the future depends only on your current state of affairs. That's the Markov assumption, or that is the first order Markov assumption. Then I have a set of goals as usual, and then I may have a start state. Now, we will study many different kinds of Markov decision processes. They will change slightly. So this is a consistent Markov decision process. I have a starting state and I want to reach a set of goals. There is another possibility where I have rewards and no goals. Absolutely no goal. There is no goal in life. I want to make the most money. I want to make the most reward. And that is the objective function. So it is not that I reach this goal, the process stops. There is no process stopping happening here. I keep doing, keep working in life, keep making the most reward. This is how most of us are if we assume that dying is really far away and is really not the goal.
What is this concept?
If dying was the goal, we will achieve our goals very quickly. Sorry.
What is this concept?
Yeah, we talk about this concept. Give me a minute. Right, so this is a consistent model. Maximize my reward, no goal. This is a consistent model. I have costs of an action, I want to minimize the cost to reach some goals and so on. And I'm going to talk about discount factor in a minute. Now, let us define the objective. But before I define the objective, let us think about what should be the nature of the solution. So in a deterministic world, what is the solution that I am looking for? The path to the goal. What I am looking for is a path to the goal. Now, does it make sense to look for a path to the goal in an uncertain world? Why not? Starting.
Path implies that you know exactly where you will end up and what the consequence of each step is. You don't know anything.
So what might happen? I take an action
And you see where you are.
and I get to different points. And based on where I get, I may choose different actions. So it's no longer a It's no longer a straight line. It is in some sense, a tree. When I take an action, depending upon where I end up, I take the next action.
But still you have paths in the tree.
I have many paths in that tree.
And it would, each path will have associated probability of, like, at any
Happening,
node.
but what I am computing a priori is not a single path. What I am computing a priori is this full tree. And another way to do this would be a policy. A policy is a mapping from states to actions. So if I knew the whole policy, can that be a reasonable solution? Get your thinking caps on. So the policy tells me what action to do in each state. So if I'm in this state, I ask the policy which action should I do. I figure out that action. I execute that action. Now what will happen? With different probabilities, I'm going to get different steps. But depending upon where I reach, I will ask the policy again, and it will tell me what should I do. So therefore, I will still be able to solve this problem.
Is there just one action?
Yes.
When we take-
So, under the assumption that we will be operating, there will be one optimal action for each state. There may be multiple optimal actions in the same state with same rewards, but any one of them works for the purposes of the policy.
So I'm not wondering how is the path is not just one line, it's a tree, or the solution is not a path, it's a tree. Because basically if you're in a state, why would you need more than one action to take?
No, you would not, but you don't know exactly what's going to happen, so the next action may be different based on where you are going to end up in the future. So if I want to characterize what's going to happen in the future today, it will be multiple branches depending upon what happens in the future.
So is that, are we not saving the whole state of the world, we're only saving part of it? And our action was going to be different from other state variables that we do not maintain?
Can you repeat that?
So I would imagine if we have the same state variables, then we will have one action.
If I have the same state, then I will have one action.
Yeah.
But the future state can change.
Oh, so basically.
A path works when I know exactly what's going to happen next, and I know exactly what I should do next. But what I should do next, if it depends on something that's going to happen in the middle, then it's no longer a path.
So other factors change my state other than the action that I'm taking, and that's why we have multiple.
Precisely. So I take an action, and nature chooses an outcome. Great. So everybody okay with the policy being a solution to the problem? So my next question is, what am I going to optimize? Now that you have already read. So in A star search or in atomic deterministic single agent, what were we optimizing? Cost to reach the goal, right? Does that make sense? Should we be optimizing the cost to reach the goal? Is there anything called cost to reach the goal if we have different things that can happen to us?
Yes, sure. Expected value, expected cost.
Expected cost. right? Cost doesn't make any sense because there is no single number that's going to happen to this. It will be an expected cost. So we will have multiple futures. In multiple futures, we will have different probabilities, so we will have an expectation. Now, depending upon the MDP we are in, it will be maximizing the reward, expected reward, or minimizing the cost, or maximizing the reward minus cost, or whatever it is. All of these are reasonable models, all of these are similar, can be easily handled. So, nothing to worry about. Now, the other parameter here is how much time do I have? How many actions can I do? So, if I can only do say 10 actions or 20 actions, and then I have to stop, that's called a finite horizon. If on the other hand, I can go on forever and keep getting more and more money, then that's called infinite horizon. And the middle point is called indefinite horizon, which says you can go on forever, but you stop when you reach the goal. So here, reaching the goal marks a stop in the process, so it's not infinite, but there is no bound on it, so therefore it is indefinite. And the last thing is called full observability. This is important. It says that I have complete knowledge of the world. I know exactly which state I am in. I take an action. Then I don't know which state I am going to be in because nature is going to choose it. So I take that action, and with some probability I get to a new state. But when I get to a new state, I know exactly which state I got into, so I can ask my policy. So there is full observability wherever I am standing. Then I take an action, I get to a new state, then I can again know exactly where I am, exactly where I reached. That's called full observability. So far so good. Yes?
If you don't have full observability, are you do you need like a completely different approach, or would there be a way to adapt?
If we get to it, it's called partially observable Markov decision processes. It's a special kind of Markov decision processes, much more difficult to solve. All the real world is really a POMDP. Pretty much everything in the world is a POMDP. They're much harder to solve. I have some examples towards the very end of the lecture, but we'll probably not get there. Depends on how fast you move. So, yes?
I didn't get the difference between finite and indefinite.
Finite horizon says that I will go on for 10 steps or a fixed number of time points, and then I will stop. Indefinite says that I can go on for as long as I want until I haven't reached the goal. As soon as I reach the goal, I stop. So,
What's the infinite one? What's the
infinite is I keep going, never stop.
What's the point of
Yeah, I'm going to get to the point in a minute. So, suppose I'm in an infinite horizon setting, which means I will go on forever, right? I want to maximize the reward, I want to maximize the money. Suppose there is one action which always gives me $1. And there is this other action B, action A, and action B, which gives me $2. Which one is better? B. But I say that I can go on forever. What is the total money that I will make if I just did action A? What is the total money I'm going to make if I just did action B?
Even better, infinity.
Twice infinity. Right? So, in some sense, as soon as we get to infinite horizons, the reward can get unbounded. So, how do we handle that? Sorry?
Did you rate a reward?
Yeah, so you can come up with other ideas, like average reward or things like that. So, another common idea for making this whole value bounded is called discounting. So the idea of discounting is that, so the idea of discounting is that money today is worth more than the same money tomorrow.
Future value.
Why is that?
inflation?
Yeah, I can put it in bank and get some interest out of it.
Your life today might not be tomorrow.
So anyway, so how we mathematically model it is by defining this discount factor called gamma, and we say that if I get reward today, it's R1, and if I get a reward tomorrow, it's gamma times R2, and if I get a reward R3, 2 days from now, it will be gamma square times R3, and so on and so forth. Now, is this, if gamma is less than 1, is this bounded? The maximum reward that I can get is R max, right? So R max plus gamma times R max plus gamma square times R max and so on and so forth ad infinitum will become R max over 1 minus gamma. So it will be a bounded sum. So this is the maximum I can get. This makes my total process bound. That's also the intuition of why there is a point to infinite horizon models. Alright. So all of these models, either if I am in goal directed indefinite horizon cost minimization, which means minimize the cost to reach the goal expected, or infinite horizon discounted reward maximization, which means go on forever, keep discounting, and are all more or less equivalent models. I mean, this is not true. One is more general than the other, but let's not worry about it. Most of the algorithms that we will get to talk about extend to both of these models, and the ideas will be the same. So it doesn't matter which one we study. Book talks more about this one, and this one, in fact, is the more popular version. It's common in machine learning, economics, operations research communities. We will talk a little bit more about the goal-directed version because it connects to what we have been doing, like A-star search and so on and so forth. Common in planning community, graph theory communities, and there are other very similar models. As soon as you can come up with this MDP description, it is very likely that the ideas that we will discuss today are going to work. Now, why is this tricky? So this is, I think, a very interesting point, and I would like thinking caps on. So, this is an acyclic MDP, which means, forget what it means. Let's look at the problem. So I'm in state P, Q, R, S, T, and this is the goal that I want to reach. I could take action A here with 0.6 probability I come here, with 0.4 probability I come here. Similarly in B I can come here with 0.5 probability and come to T with 0.5 probability. From any of these states I can take action C, which costs 1 and gets me to the goal. Action A costs 5, action B costs 10. Which action should I do? How many of you are still computing? No, it's fine. I want to make sure everybody gets this. This is important. What is the value of taking action A? 5 plus 0.6 times 1 plus 0.4 times. So I could say that value of Q, R, S, T is all 1, and value of P, if I took action A, is 6, and value of P if I took action B is 11, and therefore this is better. This action A is better. Because it has less cost. Now comes the interesting question. What would I do in this particular domain? So what happens is, with 0.6 probability, if I take action A, I come back to the same state. Now, is A better or B better? Think about this. Whoever answers has to tell me how much is B worth and how much is A worth. Okay, how much is B worth?
11.
Has anyone computed how much is A worth? How would you even compute this?
There's got to be some sort of better sum.
Is it 9?
9?
No, it's over. It's got a limit.
Sorry?
There's a limit to how.
Yeah, but what is it?
It's like,
Kind of a geometric progression.
Yes, but what's the value?
Oh, I'm feeling pretty good if I recognize it was geometric progression.
No, I'm not moving forward until I. 5 plus?
5 by
0.6.
0.4, 1 minus 0.2
Uh-huh.
plus
I think some of you should be able to do this. It's not that hard. No discount factor.
Is it 5 plus 5 by 0.4 plus 5 by 0.6?
Which is equal to? Doesn't sound right. I don't know. No one? Wow.
Well, it's,
Okay, so let's do this. It's not that hard. So what is going to happen?
well,
Let's call it
like an
QPA.
expected cost, because it could be infinite, but it's unlikely to be infinite.
No, it won't be infinite. Why should it be infinite? So what's going to happen is that upfront I'm going to pay a cost of 5. Upfront I'm going to pay a cost of 5. Then what's going to happen is with 0.4 probability I'm going to pay a cost of and with 0.6 probability I'm going to pay a cost of
Because it's
right. So we are going to pay exactly the same amount of cost,
the bracket of the same QPA.
right? So therefore 0.4 times QPA is equal to 5.4. No, 0.6 times QPA is equal to 5.4. Therefore QPA is equal to 5.4 divided by 0.6. Can you see this? Is it too far? Let me show you. So first of all, notice that I don't know if did Oren talk about expecting max and expecting min? Never. So our basic idea is that we might be able to apply in acyclic graphs do not work because we have to sum over series that's going to happen over a long period of time. But it's not hard to compute. So the cost of taking B in P is 11. The cost of taking A in P is not clear here. So
Is it 13.5?
yeah, of course. So now it's not very hard because initially I'm going to pay a cost of 5 plus with some probability I'll get to the goal and with some other probability I'll come back to the same state which is the recursive definition, and so you get QPA to be equal to 13.5. Something happened intuitively which is not clear and we'll make it clear over the next 1 hour, but this is the key point that we will need to get by the end of this class, otherwise you will not be able to do your assignment 3.
That can't be an actual cost, that has to be like an expected cost.
This is an expected cost, of course,
Because the actual cost could be infinite, you could just loop forever.
but with less and less
Vanishing
probability,
Probability.
with vanishing probability. So the expected cost is what we have to compute. Okay, so let's see. So let's try. So we could do this, we could write this equation for this specific example, but we will try to generalize this concept, and we will try to generalize this concept a step at a time. So first we are going to ask the question, which is an easier question. The question would be, given a policy pi, can I compute value of the policy pi? Okay? And value means the cost of reaching the goal, expected cost of reaching the goal while following pi. Okay? Let's look at deterministic MDPs. If my policy is the following, in S0 take A0, get to S1, in S1 take A1, get to the goal, this costs 5, this costs 1, then what is the value of the policy for starting in S1? Value of the policy starting in S1? What is the value of the policy starting in S0? Easy. Now let's do acyclic MDPs. We have done this already. So if this is my situation, with probability 0.6, I pay 5 cost, get to S1, and then pay cost of 1 and so on. What is the value of S1? 1. Value of S4, S2, 4. Value of S0, 5 plus 0.6 times 1. Sorry, 0.6 times 5 plus 1. Plus 0.4 times 2 plus 4 equal to 6. Both of these are easy questions. I want to make sure that all of you are okay with this. Anybody confused with this? Because if you are confused with this, then life will be trickier. Okay, so then now let's do the real question. So now we have to come up with some general principle, right? This is the point. Otherwise, we can't just be solving this specific problem and things like that.
Can you go back to the previous?
Sure. So now the general problem is that the MDPs can be cyclic. We are still building the atomic agent, by the way. So how do we build this atomic agent? How do we evaluate this policy? So V pi of S1 is clear, that's one. What is not clear is V pi of S2 because it depends on value of S0. And what is not clear is V pi of S0 because it depends on value of. So there is a mutual give and take in these values, and so we have to sum up these series together. How do we do that? Well, actually, it's not very hard. So what is V pi of S2? It is 0.7 times 4 plus 0.3 times 3 plus V pi of S0. Similarly, what is V of S0? It is 0.6 times 5 plus 1, and it is 0.4 times 2 plus V pi of S2. So there is a mutual set of equations that we can write. It's actually not very hard. What we have to do is just look at its successors and write an equation like this. So V pi of goal 0, V pi of S1 1 plus V pi of goal, which is 1. V pi of S2 this, V pi of S0 this.
Linear equations, simultaneous linear equations.
It's a set of linear equations. How can we solve it? Using any equation solver. Gaussian elimination. Whatever.
Nightmares about just.
You can use any existing package. Question.
Actually, the way I solved it, like you were saying, is a GP, like you keep taking that path again and again, 0.6 to 0.6, next time is 0.6 square, probability 0.6.
Right, exactly. But in
And
general, it will
eventually-
become very hard because there are multiple paths. The goal will be much further. You may have to sum over exponential number of paths. It will not scale.
Yeah, so that's
This
what
is
I-
going to scale because what you have to do is look one step in the future and write these equations and then solve. Okay. So now this is easy, but let's spell out these equations. It says if I am already in the goal, my value is. If I am not in the goal, then I will take the action pi s and with some probability reach state s prime. So recursively, so I will have to pay some immediate cost, which is cost of taking action pi s in state s and reaching state s prime. This is my current cost, immediate cost. And then I'm going to pay a long-term cost, which is recursively defined as V pi of s prime. So this is the long-term cost that I will be paying. But I may reach different s primes with different probabilities. So what do I do?
Probability increase.
Exactly. Take an expectation. That's it.
Can you explain that last part again?
Yes, absolutely. This is real life, by the way. You know, you will be I mean, this is what happens to me all the time. When I think of AI, it sort of connects. So in our lives, the value of an action or a policy is the immediate cost that I'm going to pay and the long-term cost that I'm going to pay. If I want to eat a burger today, my immediate cost or my immediate reward is really high. But the long-term reward of taking many of such actions can be quite bad.
Yeah, but there's a discount.
Yeah. Especially if you're acting forever. None of us act forever. And if you're eating a lot of burgers, probably, definitely not. So what's happening? Okay, so I am in state S. I take the action that my policy tells me, which is phi s. I reach state S prime. I pay some immediate cost, which is defined by my input, cost of taking action phi s in state S and reaching S prime, which is this. This is my immediate cost. Then I'm going to pay more cost starting in S prime. And that is defined exactly as the cost of reaching the goal starting in a state. That's recursively defined. So that will be my long-term cost. But I'm going to reach different states with different probabilities, so I take an expectation over the various states I can reach. This is my system of linear equations. Okay. Yes?
This is kind of orthogonal to the cyclic problem.
Why?
This has got nothing to do with it in the sense. This is more generic. Handles.
This is absolutely generic, but this will be able to handle cyclic problems. Everything else will not be able to. Yes, question. Sir.
So it's S3, OS3 running time. There are cardinality of S number of equations.
Yes.
And it's just how do you come up with? Is that just a
Gaussian elimination.
just a function of the equation?
Yes. Okay. So this is first approach. This is good. This can be done. But let's do the second approach, which will be more helpful to us. That's called iterative policy evaluation. It does the following. It still writes exactly the same set of equations. So like, it will say that S2 is equal to whatever, 0.7 times 4 plus 0.3 times 3 plus V of S0. So if you sum that up, it will become 3.7 plus 0.3 times V of S0. Similarly, this will be S0, this will be S1, this will be S goal. Then it says the following, that I am going to randomly assign these state values. Randomly. Let me assign S0 to be 0 and S2 to be 3 points. S0 to be 0. Let's start. I just randomly did this. But if this was true, what will be the value of S2? Now, if this was true, what will be the value of S0? You can do this computation. You will get 5.88. And then you say, if this was true, what will be the value of S2? Compute this. And you keep going back and forth, back and forth, back and forth. And at some point, you will start to see that these values are converging. And when these values have converged, you have solved the system of linear equations.
Can you get stuck in a pattern of bad answers?
No.
I mean, this is a simple graph, if you have a more complicated.
Guaranteed to converge. In the limit.
Can it oscillate? Can it be unstable?
Okay, that's not true. Technically, for most MDPs that happen in practice, under some theoretical constraints, this always happens. There are some MDPs which do not follow some criteria, and there we can get stuck. For that, you have to read my book.
What if you had actually accidentally picked a number that was much higher?
Yeah, it doesn't matter. That's the coolest thing. Give me any arbitrary starting point, 20,000 minus a million, doesn't matter. Okay, so let's formalize this. So the formalization is that it is also called successive approximation, or you can also think of it as an instance of a fixed point computation. Okay, so this is my system of equations, and what I'm going to do is that I'm going to start with some approximation of this. Let's call it V0 or Vn minus 1, and given Vn minus 1, I'm going to compute the next approximation Vn.
Is this the same idea behind PageRank?
Andrew. No. So both PageRank and these are dynamic programming algorithms. Whether PageRank is an MDP or not, I'll have to think about that. Probably. It could more. It's probably true. But I'll have to, yes.
So there has to be a mathematical concept.
Yeah, the concept, mathematical concept is called the contraction property. So in fixed point computation dynamic programming, there is a technical term called contraction property, And if your value function is a contraction property, then the fixed point has single solution, single unique solution, and you are making progress in each iteration. But I would not get anything into that. Alright. So, so notice here on the right hand side I'm going to use previous values, and here I'm going to compute the new value. This is the algorithm. So you initialize V0 arbitrarily for every state, and then do the following iteration. In each iteration for every state, you compute the new approximation Vn. Now the only other thing I need to tell you is when to stop. Intuitively, when should I stop?
With deltas.
When the values are not changing by much. So I will look at how much the value changed. Let's call it residual. So that's the difference between Vn and Vn minus 1 for every state. I will take the max residual, and when the max residual is less than epsilon, I will converge, I will stop, and this is called epsilon consistent value function. This is my termination condition. Too many concepts, but the idea are too many terms, but the ideas are the same. Any questions about iterative policy evaluation?
What's the order of this?
What is the time complexity?
N into.
So the time complexity, you should tell me the time complexity of doing this computation.
That's N. For each.
How many successors can my one state have?
S.
S,
Yeah,
S,
total,
S,
total,
S,
total.
right? So this will take order S time. I have to do this over
S.
all states in one iteration. So one iteration is S square.
Total S square.
One iteration is order S square. The question is how many iterations? And for that, it depends on the MDP. So for infinite horizon discounted reward MDPs, it is a polynomial in SA and 1 over 1 minus gamma. For the other versions, the bounds are not very good, but it's guaranteed to converge.
And it gets worse from there.
We're solving hard problems.
Because it's going to be better than S cube always.
No.
Because the other one is S cube cosine.
Right. So this is not going to be better than Gaussian. So the question is, I mean, it's not provably better than Gaussian. So why are we doing this? We are doing this because this will we have not yet solved our problem, which was which action to take. We have figured out if I knew the actions, what is its value. So my input here was the policy. Where did I get the policy from? That's the question. We have to compute the policy. So these ideas are going to be helpful when we are going forward in computing the policy. Give me a minute, we'll get there. Any other questions on this? Okay. So now, let us go from policy evaluation to the algorithm of the day called value iteration. Has any of you heard the term value iteration? Okay. So if this is the most important slide of this lecture, but I think you are already ready to understand this. So you probably already understand this. So I don't have a policy. This is what I want to compute. So what I'm going to start with is a definition of V star of S. It is defined as the optimal cost, that is, the minimum expected cost to reach the goal starting in this state. Notice that this is different from V pi, which was the expected cost to reach the goal starting in state S while following policy pi. Now we have no policy pi. There is no fixed policy that we are going to follow, so we have to do the minimum expected cost to reach the goal. Okay, you have to compute the optimal cost. Okay. Again, if it is the goal, the V star of S is 0. Because I have already reached the goal, I don't have to do anything. Everybody okay with this? Okay, so now I want all of your concentration for this slide and then you can sleep. So if I take action A in state S and I reach S prime, what is the immediate cost that I will be paying?
Cost of
CSA S prime. What is the best long-term cost that I can pay?
V star S prime. No, V star S prime.
No, I mean, I'm not saying right or wrong. So everybody has to think through this. So I will pay some cost up front, which is the cost of taking this action. And then I will be paying some long-term cost to reach the goal. What will be that? What will that be?
The best to reach from S prime.
The best that I can do from starting from S prime, which will be recursively defined as V star of S prime. So this is the total cost that I will pay if I took action A in state S and reached S prime. But there are many S primes that I can reach. So what do?
Wait and see.
Take an expectation over all the S primes that can happen after this action, which is the weighted average expectation. So far so good. Now comes the difference. I don't know which action should I be doing. Which action should I be doing? The best action. Minimum expected cost to reach the goal. So what do? I take them. This is my system of equations for a Markov decision process. If you got this, you got this class.
This looks the same as the game algorithm of expectations.
But is there a minimum in the expectation maximization step? For the max? There's an expectation step. Parameter estimation. So, yeah, we will talk about EM, but I do not know if there's a connection between the EM algorithm and this, honestly.
Does this assume like no negative costs?
Yes.
No. However, it does assume some well-formedness in the MDP, which is that you cannot have negative cycles.
Okay.
Because if you have negative cycles, then you can keep decreasing your cost ad infinitum.
Yeah, there's an equivalent.
And there are other, and then it also assumes that it is possible to reach the goal with probability 1. Because if it is not possible to reach the goal with probability 1, then what will happen is that you will keep incurring lots of costs. So there are some tricky situations, but we will not worry about it.
So you don't have a pi in this case. So you evaluate for all possible actions
Yes.
and then choose the minimum.
Yes.
But in each S prime, can you take an action? Like every state can have a set of possible actions, not all actions.
Right, and that will be computed by recursively by V star. That's why it's a recursive set of equations. You look one step in the future, but
So this capital A would be the set of actions that are possible in S,
yes,
that are possible in S,
Yes.
not in general all actions.
doesn't matter. If it is not possible in S, then you will not get any of it. You will not have a transition. So okay, so if you have understood this, and I tell you that okay, now you are in infinite horizon discounted reward setting, then what's going to change? So there is no goal, you have reward at each step, and you want to maximize your reward forever, and there is a discount factor. So what's going to change? One at a time, Kiran.
Gamma times V star S prime?
Gamma times V star S time, what else is going to change? So me,
We're going to insert the reward at
you will have a reward instead of cost. What else is going to change?
next.
You have to maximize that. One more thing that has to change. There is no goal. So this will be the Bellman equations. Oh, by the way, these are called Bellman equations. This was developed by Richard Bellman in the 60s or 50s, operations research community. That is where this model comes from. It was acquired in the AI community in the 90s, and so ever since then we have made it our own. So it doesn't matter. It's a probability distribution. I got this slide from some other set of deck. My apologies. It's the same thing. Transition function. So now we have reward. We have a gamma times for discounting. We have max, and we don't have a base case. So by the way, this term, which are without the minimum, we will call it Q star. So it says what is the optimal expected cost if the first action I do is A, and after that I do everything completely optimally. And V star of S is the minimum over all actions for Q star of S. Okay. Now, get your iterative policy evaluation caps on. Can we, oh by the way, is this a system of linear equations? Is it? What is non-linear about it? Exactly. So it's not a system of linear equations. So this we cannot solve using Gaussian elimination, but we know how to handle this using iterative policy evaluation. So let's call the value iteration algorithm. So what we will do? We will start with any value and just do successive refinement. So iterative refinement. So this is my system of equations. I will start with some v0 function or vn minus 1 function, use this in my right hand and generate a new vn approximation. And keep doing this and converge. So the algorithm is rather straightforward.
So the proof of it, the refinement working with min.
Yeah, again you have to prove that this operator is a contraction operator. So let's not worry about the proof. So here's my example. This is a more complicated MDP, but let's do a part of this. So let us suppose that I want to do iterative refinement at S4. So the operator that we use is called the Bellman Backup operator. So it says my current value is 0 for S goal and 2 for S3. I can take action A40 or action A41. So this is action A40, costs 5, gets me to the goal. This is action A41, costs 2, with 0.6 probability gets me to the goal, with 0.4 probability gets me to S3. So what is a Q of S4 A40? What is the next approximation for the value of A40? It's what is the value for A41? Two plus 0.6 times and 0.4 times 2.8. Now what is the new value for S4? Will it be minimum over all actions or maximum over all actions? Or expectation of all actions? Obviously minimum. We want to do the best we can. So we take the minimum and so we get a new approximation 2.8. That is called a Bellman Backup operator. And now the algorithm is rather straightforward. Oh, and by the way, as of now, as of this information, what is a better action to do? A41. Because this is the action which is giving me the best value. We will call it the greedy action. Now, it's very important to note that these values are completely random. So this greedy action is probably very random. But over a period of time, as we do more and more of this, these values will become better and better, and the greedy actions will become better and better. And when it converges, we would have converged to the optimal or very close to optimal value functions and optimal or close to optimal policy. Okay? So this is the algorithm. Again, the algorithm is rather simple. This was thought of way back in 1957. Initialize value of each state arbitrarily and repeat. For each state, compute the next approximation using Bellman Backup as we just did. Again, compute the residual, which is how much the value has changed, and make sure that the max residual is less than epsilon. And whenever the max residual is less than epsilon, I have found close to optimal value function, and I can return the greedy policy, which is whatever is minimizing this. Okay, so this is a run on this particular example that I started with, say, this value function, which is how far the goal is. So 1, 2, 2, 3, 3. And then I kept doing this over and over, and as you can see slowly, these value functions seem to be converging. A couple of quick comments. So this is a decision theoretic algorithm. Why is it a decision theoretic algorithm? Because it uses the principles of decision theory, about the probability of various outcomes and expectations and what is the best action in order to make this thing work out. It is a dynamic programming algorithm because it is memorizing the value of each state in the previous iteration and reusing and using that in order to do the next layer. So it's a dynamic programming algorithm. You can talk about it as a fixed point computation, and if you remember your Bellman-Ford algorithm from shortest path. So there was Dijkstra's and there was Bellman-Ford. This is the probabilistic version of Bellman-Ford. What was Bellman-Ford doing? It was saying all the succeeding edges, tell me your values, then I'm going to compute my value. This is exactly what it is saying. It's a message passing algorithm. It is saying, I am at this state, tell me your values, I'm going to do the expectation and the minimization myself and figure out what is the right action for me. Then if your values change, you tell that to me again, I will redo my computation. That's it. It just keeps passing these messages back and forth, back and forth, back and forth. Eventually it converges. That is the algorithm. You can compute the time complexity. So one iteration for each state, you have to do a Bellman backup. One Bellman backup requires you to go through all the actions. For each action, you go through all the successes. So you can have S successes, all actions S times A, all states in an iteration S squared times A. So the time complexity of one iteration is S squared A, and again the same issue with the number of iterations. For many models, it's polynomial in this, and for some, it can be worse. Here's another interesting property. I don't think it's that critical anymore, but the point is, if my value function is a lower bound of the optimal, I will stay a lower bound. So I'll keep doing these backups and I'll keep getting up and closer to the optimal, but I will never exceed it. This is called the monotonicity property. Or I can start from above the value function and I'll keep decreasing it, but I will never shoot the optimal. Of course, if some states are lower, some states are higher, then they will keep doing this and eventually come back to the optimal. This has a ton of applications. Whenever we have to do long-term decision making under uncertainty, Markov decision process is the first algorithm that comes to mind. It is used in stochastic games, and that we will see in our assignment. Very valuable for robotics, navigation, helicopter maneuvers, finance. This is pretty cool. Okay, you have expected value that you can make. Your market can fluctuate. It has a probability distribution. You have actions that you can take. You can invest now. You can get it back. Those kinds of problems over a long period of time get modeled as MDPs. UW has a very interesting application for this. There's an industrial engineering professor, Acyclic. He has been working on radiation planning for cancer. And the idea is that if you send the radiation in this direction, it will kill more of the cancer cell, but it may also kill some good tissue. And based on where you radiated, the tissue will respond and the organs will respond in a certain way. So you have probability distribution over the future, and you have to make long-term planning of which direction and how much intensity do you do your radiation. You use Markov decision processes for that. And there are many, many examples. I can't get into all of these. Even for bidding decisions, how much do I bid, because it's a long-term game that I'm playing. Aircraft landing, which runway do I land? There's probability distribution of what happens in the future, and so on and so forth. So, Markov decision processes are an extremely useful model. Not very easy to solve, unfortunately, because we already talked about the time complexity to be polynomial in the state space. State space can be huge. So it is tricky, but we will do an assignment where it's not that. We have 10 minutes. I'm thinking, what should we do? What I'm going to do is talk about extensions of what we have done so far, but not discuss them in detail. So, so what we just learned is the atomic agent. In fact, it is the atomic agent which is not even doing search. this is the sort of sad thing, right? Search is everything. But what is the atomic agent doing? It is saying go through all the states to Bellman backups. Go through all the states to Bellman backups. What if a state is not even reachable from my start state? Am I not wasting time? So if I knew how to, so like in A star, what did we do? We started from the start state, used the heuristic function to try to get to the goal faster. You can have the same ideas within Markov decision processor. We will not get into this. But the idea there is, if I have the start state and a heuristic function, then how do I exploit that heuristic function? And the algorithm is called LAO star. So A star is for deterministic graphs. AO star is actually an intermediate algorithm developed in the 70s that is for these graphs, MDPs, but acyclic. And LAO star was developed in the 90s, late 90s, called loopy AO star, and that is when you have cyclic graphs. So that is one thing that you can do. Now, in classical planning, we use planning graph to generate a heuristic function. If our language was strips, or the new language is called PDDL, I don't know if Andre got into this, it's called Planning Domain Description Language. So similarly, in probabilistic planning, we have a new language called probabilistic PDDL, and you can automatically use planning graph-like ideas or other ideas to generate a heuristic function, and people have studied that. Another idea is hierarchical MDPs. So suppose I want to go from here to, say, Washington DC, where I was last week. I don't really go through all states and think about all the actions I can do. I know the structure of the policy. The policy is, first I'm going to go from my home to the airport. Then I'm going to go from the airport gate to the, say, internal gate. Then my airplane will take me to Washington DC. Then I'll go from the airport to the hotel, whatever. So now what I did, I broke my problem, I decomposed my large problem, my final goal, into a series of sub-problems. And then I can further decompose this, and then further decompose this, and then solve the problem only like the smallest problem at the last bit. So this is called hierarchy, or subsumption hierarchy, or a hierarchical solution, or hierarchical planning. And this is a common solution for everything, not just for probabilistic problems, but for deterministic problems. How do I have to decompose a large problem into a subsets of problems, and then decompose it further and further and further. What I'm going to talk about in week 10 or week 9 is a notion of reinforcement learning. So up until now we have been assuming that we have all the model ahead of us. We know exactly what the probability distribution is, we know exactly what the rewards are. Actually, that's never a real assumption. That's always wrong, more or less always wrong. In blackjack, with infinite deck, yes. When you start doing 8 deck problems, life will become trickier. So, what do we do in those circumstances? Well, we have to learn the model one way or the other. How do we learn the model? That gets us into the domain of reinforcement learning, and we'll talk about it. It's very close to how a baby grows up in the world. When a baby comes out, they may have some instincts, but they still haven't figured out the model. They have to do some actions. They get some reward for those actions, like they get milk, or they get toys, and maybe even negative reward. And based on those actions, they figure out what is the best action to do and what is the model of the world. So that is called reinforcement learning. So the parents, the surroundings reinforces good and bad actions by giving rewards. So we'll talk about that in a couple of weeks. And lastly, let's take a couple of slides and talk about partially observable Markov decision process, since this has come up a couple of times now. So we are in a framework where we have noisy sensors. So we cannot observe the whole environment, we can only observe a part of the environment. So the change that gets made is now our environment is partially observable and our sensors are noisy. So how do we plan that? So imagine that I want to go from the green dot to the red dot. If I could fully observe which state am I in, and I had good control about, so this is the deterministic version, right? I knew exactly where I could, exactly what my outcome of the action is, then I will go straight through this thin walkway and get to the red dot. This arrow indicates which direction should I move. If, however, I try to go in the front, with some probability I may go on the side. Then notice that here I am choosing to go out of the walkway. Why?
Scared you'll get stuck.
Exactly, I could collide into these walls and that will be a low reward region. I might die because I have uncertainty in my action outcome. So it's better to try and get out of this thin walkway and have come back to the red dot from another path. Make sense? Sorry? Here what happened is that my actions are not in my control, they are noisier. So as I take an action, I may go in some other direction with smaller probabilities. So here, by going through this path, I might get stuck, I might collide with these, and that will be a low reward region. So it's better to come out if it's a smaller way to come out. However, in partially observable scenarios, it's even more interesting. Suppose what the robot observes is only what it can observe around it and has no idea where it is in the full map. Then what should it do from the green dot? It knows the map, but it doesn't know where it is. So by looking at the fact that there is 4 corners that are visible to it, does it know where it is? Right? Because this structure is not visible, is not present anywhere else. This is different, right? So it knows exactly where it is. What does it not know? Which direction is it facing? So it can distinguish between up, down and left, right, but it can't distinguish between left and right. So what should it do? It has to locate itself. How does it locate itself? By going to a corner. Why?
Go find a unique feature.
Because you have to find a unique feature so that you can exactly locate yourself. Here you can't figure out, here you can't figure out. Here on the other hand you can figure out, because this one is much longer, this one is much shorter. So it goes straight to the closest wall. This would be either this or this. And then it takes a right. If it takes a right, either it will go in this direction or it will come in the left direction. And then as it reaches the end, it looks around and it's figured out whether it is in this corner or this corner, then it can come back and do any policy. Yes? You have a question? No. So this is the solution. If you're in a partially observable environment, what happens is that you not only take actions that give you the most reward or take you towards the goal, you also take actions which give you more information, because then you might be able to reach the goal better. And again, you have to compute the value of these information gathering actions, and we did a little bit of this in decision theory early in the class, but that was only for one action. Here we have to interleave this whole process. Now really it is like an MDP, it's not very complicated, but the problem is that I don't know the state. So value of a state makes no sense. What I know is a probability distribution over states. I know that I may be in this state with this probability or that state with that probability, but I don't know exactly which state am I in. So we will call my knowledge that I have today, the probability distribution over states, as a belief. It's a belief. Now I believe that I am in either this state or that state with different probabilities. I don't know more. So instead of computing a value for a state, I compute the value for a belief. And the equations are pretty much the same. Value of a belief is max over all actions, the immediate reward, plus gamma times the value of the next belief and the probability distribution and so on. But notice that what is the size of this belief space? If I have n states, I could have any probability distribution over those n states as my belief. So the size of the belief space is uncountably infinite. So now I am in a very difficult problem. The formula is very clear, but really computing this is intractable or really, really hard because this belief space is uncountably infinite.
What makes it uncountable? Is it the
Because probability is between 0 and 1, you can, sorry?
Is it because the probability distribution functions are continuous?
Yeah, exactly,
Because
because,
you can add any countable number of discrete states and you're still countable, but
but the
somehow you-
distribution, the probability distribution can be anything, right?
Okay.
It can be 0.001 in a certain state or 0.0011 and so on. Right, so let's not get into how we solve them because I don't think we will have any time for this. I just want to mention that if you start thinking about any real problem where you have to act over a long period of time and there is uncertainty in the domain, it will more or less be a probability. So if we could solve this general problem, we will solve all or most of intelligence AI problems. It's not, it doesn't handle multiple agents, but any single agent problem we will be able to directly solve. Unfortunately, these natural problems are really, really hard to solve, and therefore we are never able to solve a general problem very easily. But it has applications in neuroscience, so people are thinking about how we think, how we make decisions, and we have POMDP models for our own decision making. Assisting elderly, there have been, we have built a robot that helps the elderly. If you want to build an application over your phone to figure out what you are going to do in the future, and therefore you prefetch that application, or you understand the user, all of these are POMDPs because you never know exactly what state user is in, you have a probability distribution. So this comes up in spoken dialogue management. Like you call your airline system and say I want to go from Seattle to DC, then it will figure out what I said, and it will figure out what my intention is, and it will never know exactly, so it will only have a distribution over my state, and then it will take its actions based on the distribution over my state. And sometimes it will ask me to double check, like, do you want to fly from Seattle? Why will it ask? If it is uncertain, then it's an information gathering action, so that whatever it does in the future, it gives me a good reward, and so on and so forth. I think we should end at this point, but we will, in the last class, if we get there, I'll talk about an agent that uses POMDP that we have worked on ourselves.